Okay, let's talk about ways to solve ordinary first-order differential equations numerically. The easiest way is Euler's method. So first we need to set up our differential equation. So our differential equation is going to be defined by some expression, dx dt, equals some function of both x and t. If it were a function of only t, we could solve it with Simpson's rule or some other numerical integration formula, but it's a function of specifically x and t. And notice there's only one derivative. We've got one independent variable t, and then the dependent variable x. So we've specified the main part of the differential equation, but we still need to specify an initial condition since this is a differential equation. So there we go. We've got our initial condition. There's some t0. Doesn't have to be 0. Could be any value. And we know the value of the function x of t at that point. So we pick our t equals t0, and we know the value of the function right there. Okay, now we want to draw the entire function line, but for now we just have a single point. So we want to know how can we extend our knowledge of this function from the single point to the rest of the curve. Well, we can do a Taylor series expansion of the value of the function around the point t0. And so if we just do a first order expansion, we get x of t0 plus t is going to be equal to x at t0 plus dx dt times some function, times some small interval delta t, for some small delta t. Now the thing is, we know what dx dt is. It's just the function that's defined in our differential equation. So this is very easy to calculate once we have our initial point. So we calculate what that derivative is, and the derivative is the slope. So we know the slope of the function, and we follow that slope of the function up and see how the function changes over some interval delta t. So we go over delta t, and we have a new point. That point right there is just x at t0 plus f of x and t times delta t. So there we go. That is our guess for the next point of the function. Now we're there, we can find the derivative at that point by plugging into our function, and that's it. We just keep repeating that. We keep repeating it. We can now go out to t0 plus 2 delta t and keep on going as long as we want to. Now, of course, this is not going to be a great estimate unless delta t is quite small. It turns out that this method is only order delta t. So we'll approximately have the error when delta t is reduced by half, and that's locally. Globally, things that is the global error overall. But if you get off a little bit, that error keeps accumulating at each point. So you do need to have a fairly small delta t in order to get good answers. So let's take an example. Let's define our f of xt equal to 3 times square root of x plus t cubed. And we'll say, okay, our initial point is t equals 0.2, and we'll say at that value the function is 0.1. We can really decide anything we want to. The specification of the initial point is independent of the definition of the function. Okay, so we got that, so we choose some delta t. Let's choose 0.1, why not? And then what we get is, what we're solving for is x at 0.3. We know x at 0.2, we want to solve it at 0.3. So then we evaluate the function at x of 0.2 and at 0.2 and multiply by delta t. Now of course, x at 0.2, that's what our initial specification of the problem is, and so that's just 0.1. So we just need to plug 0.1 and 0.2 into that function, 3 times square root of x plus t cubed. So we can plug that in, and we get a value. Notice that what's in the square brackets is the slope at that initial point. So we multiply the slope times delta t plus 0.1, we get a solution for the first point using Euler's method. So that's great. That's the simplest way, but it turns out to be not efficient. It's not that efficient because we're not using a very good guess for the slope. So we want to look at ways we can use better guesses of the slope. Algorithms that are order delta t squared, that scale with the square of the change in our delta t. Okay, so Heun's method is one fairly straightforward second order method where we're essentially including the quadratic terms. It's not that clear from the definitions that the quadratic terms are being included, but you can see they are in the end. We'll talk a little more about it when we talk about general Runge kind of methods. Okay, so again, we specify the problem. Same as before, we have some dx dt, first order differential equation is equal to some function of x and t, and we have some initial conditions. So we start out with our initial conditions, we start out with our single point that we know, we want to sketch in the rest of the function. So we start out in exactly the same way as Euler. We say, okay, the value of the function at this new point, at t0 plus delta t, will just be equal to the value of the function at that point plus the derivative, which is just f of xt times dt times our change in our independent variable. So yeah, we plug that in, we find the value of the slope, and then we go out to the new point, find the new point, and for Euler that's where we'd stop. But for Heun's, that's just the first step. This is the predictor half, and then we still need a corrector half, where we go back and correct to get a more accurate value of the slope. So what can we do? So here's our function again. We're using delta t equals 0.1 as well. And so x of 0.3 is equal to what it was before. Remember, this first step is exactly what we did for Euler. And we get a first guess for what x at 0.3 is. But we want to refine that guess with a better estimate of the slope. So what we do is we take the value of the slope at that new point, and then we average the new slope, our blue line, with the old slope, the red line, and get a third slope, the average of those two. So it's the average of those two slopes at the two different points, and since those are the slopes of the endpoints, the average is a better estimate for the slope in the middle. So we take that average slope and we take a full step. So it's the same t0 plus delta t that we used to evaluate Euler's, but now we're using this more accurate slope. So plugging that in, we need to know what the value of the derivative is at that new point, and we can get that out. The derivative has increased a little bit, the function's increasing, and then we average the two slopes together. The first slope is the slope we got before, the second slope is the new slope at the end point, so we average those together, multiply by our delta t, grind through the calculations. We have our average slope, 1.15, which is larger than the initial slope that we guessed, 0.9567, and we get our new value. Right, so this should be more accurate because we're using a more accurate value of the slope. Now there are more than one methods that are second order, so let's take a look at the midpoint method, which is another second order method. So again, we have our definition of our differential equation. We've got dx dt equals f of xt. We have our initial point, exactly the same as before. And so we got that point, and we're now going to try to solve for the rest of the points. So we start out with the same idea. We want to find out, we do a Taylor series expansion, we want to find out the value of the function slightly further along. And so we've got that. But what we do is we don't go out for the full step. We go out only halfway. So we go out to a half step, and we find the point at that half step, and then evaluate the slope at that half step. So we plug in. Now, instead of doing a full step of Euler, we're doing a half step of Euler, and we get the slope. Notice the slope is the same as if we're doing the full step. We're still along the same line, but we're only going half as far along that line. So we get a value of the function at the half step, and now we can compute what the derivative is at that halfway point. So this should be a more accurate value of the derivative than when we were starting out, because we're including some of the change that happens along the slope of the curve. So we've got that half step, and now what we do with that slope that is computed at the half step, so we can go through 1.169. If you recall, if we average the beginning and the end slopes in Heun's, then it was 1.15. So this is actually fairly close to the slope we're using for Heun's. And so then we can just move that slope down and use the same slope we computed at the midpoint, but use it from the first point, and then we take a full step with that slope measured at the halfway point. plug it in, get that, just grind through the math. We've got our new slope times 0.1 plus the initial value, and we get another, also more accurate value for the function at 0.3. This is also a quadratic, it's an order delta t squared, a second order quadratic method, because we're using a in-between estimate of the slope. We're using information in the middle of the segment instead of at the beginning of the segment. If you recall with the central difference, when we took a look at the slope in the middle, we're able to include the second order effect. So if we compare this to Euler, we can see it's a little different than Euler. If we compare it with Heun's, which is also a second order method, we can see we get a value pretty close to Heun's. So those two more accurate methods agree with each other. And we can see that we're getting fairly close to the right answer now. These two different methods agree fairly closely. So that's a basic walkthrough of the graphics, visual display, and some examples of these three methods. The Euler method, the simplest method, because all we're doing is a linear Taylor series expansion, and then Heun's and the midpoint methods, which are both quadratic methods. We didn't explicitly include the second order derivatives, but as we'll see next time, we sort of implicitly included them and wrapped them into this by using information of the slope halfway across.